Imagine a world where structures can react and adapt to their environment. Bridges that can withstand earthquakes with minimal destruction. Buildings that can ensure stability and comfort to the ones living inside by adjusting to wind gusts. This vision of future is becoming a reality thanks to a class of materials known as magnetorheological elastomers, or as known as MREs. MREs are a fascinating blend of rubber and magnetic particles, but what truly sets them apart is their ability to transform. When exposed to magnetic field, their stiffness can change, making them ideal for applications that require dynamic control. Now, predicting the exact behavior of these materials under various conditions is very difficult. Traditionally, engineers have relied on complex mathematical models. However, these models can be very inconvenient when trying to capture the finer details of MREs. It's like trying to solve a Rubik's Cube with a single rigid approach. But what if we could leverage the power of the latest technology to easily predict how stiff and bouncy this material can become under different conditions? This is precisely what this research is all about. In this presentation, we'll explore how machine learning is used to make predictions by learning patterns from the data given to them and how they can revolutionize the way we predict MRE behavior under various conditions. To describe MRE behavior, engineers have relied on parametric models like Kelvin-Boyd and Bookwan models. These models focus primarily on the external force displacement response, or the hysteresis loop of the material. While they offer useful and valuable insights, they often lack the details of MRE's internal structure due to their nature of parametric models. Furthermore, complex analytical models have been developed to understand their behavior at a deeper level. However, these analytical models require detailed mathematical derivations and are often computationally burdening. A significant problem of these traditional modeling techniques is actually their inability to capture the non-linear behavior of MREs within the linear viscoelastic limit, or what we call as LVE limit. This results in challenges when trying to accurately predict their performance under various conditions. Now, this is where machine learning steps in. This research proposes an alternative approach utilizing machine learning algorithms like artificial neural network, ANN, or the extreme machine learning, which is called ELM. So, unlike parametric models, these neural networks can learn complex, non-linear input-output relationships without the need for parameter identification. These models also do not involve any higher-order mathematical derivations. Building upon this knowledge, our specific objective is to develop a machine learning model which utilizes ANNs and ELMs that can predict two properties of MREs, which are storage modulus and loss factor. This model will also consider the shear strain as deformation applied, but will also take in a key additional factor, which is the magnetic field strength. The constant frequency will also be maintained during testing. Now that I have explained the problems of the current methods and the objectives to tackle the limitation, let's now explore the methodology used in this research. First, let's discuss the creation of MRE samples. This experiment followed a fabrication method documented by this research. As you can see on the left, the foundation of MRE is natural rubber, as sourced from Malaysian rubber board. To introduce the magnetic responsiveness, this fabrication uses carbonyl ion particles, with an average size of 6 micrometers obtained from BASF in Germany. The specific composition of MRE, an additional element which is epoxidized palm oil, is added to disperse the ion particles throughout the mixture, which will ensure uniform distribution. To improve the MRE's properties, specific ingredients are added during mixing. This included zinc oxide, stearic acid, sulfur, and CBS for better strength and stability. This fabrication also incorporated xanthoflexicoline and a synthetic polymer to enhance the MRE's resistance to environmental factors. Through careful mixing, the MRE samples are created, which will be used for rheological testing. Now that the MRE samples are ready, we use a tool called rheometer to conduct the rheological testing and see the MRE properties for storage modulus and loss factor. You also see how the MREs behave under different magnetic field strengths. In order to know how much the MRE can be stretched and how stiff it can become, there are three parameters that need to be considered. The first one is shear strain, which essentially tells us how the MRE sample is stretched or squeezed. The second one is sweep frequency, which tells us how often the stretching or the squeezing on the MRE happens. The last one is sweep current, which is essentially the most crucial one for this experiment as it controls the magnetic field strength that the MRE experiences. A stronger current basically means a stronger magnetic field. The rheological tests reveal interesting results. As you see here, the stiffer the MRE, which means the higher storage modulus, the stronger the magnetic field is. This is because the tiny ion particles inside the MRE line up with the magnetic field, forming stronger chains and resisting deformation. Next, you can also see here how much energy the MREs lose during deformation. This is called the loss factor. At low strain levels, it remains stable, but at higher strains, the interaction between rubber and ion particles gets more complex, leading to this up and down pattern. Now that we have all this experimental data in hand, which are crucial because we want to compare this experimental data and simulation data later on, it's now time to use machine learning. One method we use is called the artificial neural network, which is ANN, and another method we use is extreme machine learning, which is ELM. Inspired by the brain, ANNs are network of processing units. In our case, the ANN learn how the MRE behaves by analyzing the relationships between three things, which are the magnetic field strength, the amount of stretch applied, and the resulting stiffness and energy loss that we measured. The network learned these connections through a process called backpropagation, which allows it to adjust itself repeatedly until it can accurately predict the MRE behavior under various conditions. Similar to ANNs, ELMs use a network of interconnected units. However, ELMs take a unique approach by pre-assigning certain connections, which are called weights, within the network during the setup. Research has shown that this pre-assignment simplifies the training process for ELMs compared to ANNs. In ELMs, the connection between the hidden and output layer are calculated based on these pre-assigned weights, making it more effective when we have a large amount of training data, as in this case. Now, to train and test our models effectively, this research followed a careful data splitting strategy as outlined in this reference paper. As you see here, the data was divided into three sets, which are training, testing set 1, and testing set 2. The training data, which consists of 70% of the total data, form the basis for the models to learn the relationships between the magnetic field, stretch, and also the MRE properties. Testing set 1 acted as the first test. It contained unseen data, which is 30% of the total data for the models to predict. This allowed us to see how well they could handle new data within the range they were trained on. Finally, testing set 2 presented a tougher challenge. This set included data points which are 20% from the total data with magnetic field strengths outside the training range. By incorporating training set 2, we could evaluate the model's ability to extrapolate their knowledge and predict MRE behavior under even wider magnetic field conditions. To achieve the most accurate predictions possible, this research optimized several key parameters within both ANN and ELM models. One important parameter is the activation function, which essentially determines how the model translates its internal signals into outputs. This research explored different activation functions, for example, logarithmic sigmoid function for ANNs, as mentioned in the paper. Another crucial parameter is the number of hidden nodes within the network. This value influences the model's complexity and its ability to capture detailed relationships in the data. This research experimented with a various number of hidden nodes for both ANNs and ELMs, training each models multiple times to ensure consistency. Now, let's take a look into how these models performed. We used two key measures, which are RMSE and R-squared, to assess their accuracy on all datasets for both storage modulus and loss factor. Since our models predict two outputs, storage modulus and loss factor, we assessed their performance for each one separately. The proposed models included three ELM configurations, named ELAN sigmoid, ELAN sine, and ELAN hard limit, each utilizing 50,000 hidden nodes and employing different activation functions. Additionally, we developed two ELAN models, AN5 and AN7, differentiated by the number of hidden nodes, 5 and 7 respectively. The accuracies for all models are presented in these tables. Notably, the models perform much better on training data and testing set 1 compared to testing set 2. This difference in accuracy across datasets emphasizes the importance of using unlearned data outside the modeling range to truly assess a model's ability to generalize and avoid overfitting. For example, the ELM-SIG model had negative R-squared values for unseen data, which is training set 2, indicating poor performance. In contrast, models like AN5, AN7, and ELMHL perform well on training set 2, suggesting that they can generalize to new data. Hence, based on these findings, we focus on comparing AN5, AN7, and ELMHL using data from training set 2 as shown in the graphs for storage modulus and loss factor, respectively. Now, let's take a look at the results of the storage modulus first. It shows from the graph that AN7 excelled in predicting storage modulus, especially at specific shear strains. It also agreed well with the unseen data pattern. This is supported by this table here, where AN7 has the lowest RMSE for training set 2. For loss factor, the models had varying results as shown in these graphs. It shows that AN5 performed well in predicting storage modulus. Meanwhile, ELMHL outperformed AN5 in predicting loss factor. The impressive performance of ELMHL is evident in this graph, where the model closely replicates the pattern of the experimental data. Nonetheless, AN5 also demonstrates a strong performance. Interestingly, both AN5 and ELMHL models exhibited similar prediction capabilities for the extrapolated magnetic flux density as shown in the graph. Now, let's shift our focus to the material's rheological properties. These properties can be broadly categorized into two responses, which are linear response and non-linear response. Typically, the linear response is observed at low shear strain, meanwhile the non-linear response is more prominent at higher shear strain. A crucial material characteristic within the linear response is the linear viscoelastic limit, which is called as LVA limit. We analyzed both experimental data and predictions from our machine learning models, AN7 and ELMHL, to determine this limit for various magnetic field strengths. Interestingly, the LVA limit tended to be higher for stronger unseen fields, which is extrapolation, compared to weaker family fields, which is interpolation. This highlights the Payne effect, where stronger magnetic fields shorten the predictable region within the MRE. The AN7 model emerged as the champion in predicting the LVA limit. While ELMHL also performed well, AN7 consistently showed a smaller difference from the experiment, especially for unseen fields. This solidifies AN7's position as the superior model, as a model's true strength lies in its ability to handle new data, and AN7 performs better with unseen magnetic field strengths. Once we have established the LVA limit, we now analyze the accuracy of AN7 in both linear and non-linear regions. We compare the model's predictions with experimental values across various magnetic field strengths for both regions. As expected, the linear region was shorter than the non-linear region. This translates to lower error rates, which means low RMSE, in the linear region compared to the non-linear region, as shown in this table. This table also reveals impressive performance for both familiar and unseen magnetic fields. Notably, both unseen fields exhibited exceptional accuracy in both linear and non-linear regions, with correlation coefficients R-squared exceeding 98% at 0.538t. All familiar fields also showed satisfactory performance, with most R-squared values exceeding 90% in both regions. Additionally, the model consistently predicted the crucial linear region with high accuracy, which means RMSE below 0.05 MPa for all fields. This emphasizes the model's ability to accurately determine other key variables. Therefore, it is evident that AN7 outperformed ELMHL based on the analysis of LVA limit and model accuracy across different regions and magnetic fields. In summary, we successfully fabricated MR elastomers and studied their response to different levels of strain and magnetic fields. We measured how stiff and elastic the materials were, which means the storage modulus, and how much energy they dissipated, which means the loss factor. Machine learning models were then developed to predict these properties based on the applied strain and the magnetic field. We found that some models perform well on initial data, but they struggle on unseen data. However, the ANN7 model excelled at predicting both stiffness and the critical LVE limit even for unseen magnetic field strengths. While another model, which is the ELMHL, did well with energy dissipation, ANN7's overall accuracy and ability to handle new data make it a superior choice. This research shows that machine learning, particularly the ANN7 model in this case, can effectively predict how the MR elastomers behave under different conditions. Ultimately, the problems are tackled and the objective of this research is achieved. The goal is to create a model that is both accurate and efficient, which will allow us to design MR devices with specific functionalities for various applications. So with that, thank you so much for watching this video. I hope you find this video insightful. Thank you and have a nice day.